Okay, in this video what we're going to do is analyze this MOSFET circuit, which I've drawn out already, and develop a small signal model for it, basically. So you got a voltage source coming in, which we've broken its input signal into two pieces. It's sort of steady, or not steady state, but it's bias voltage, kind of its large signal voltage, and its small signal voltage right here. That voltage source goes through a resistor R1 into the gate. Then that MOSFET runs, and there's three other resistors, and the voltage we're interested in is across R4, the sort of output load resistor in some sense. And remember, what we're doing here is small signal analysis. And that means, and again, refer to lecture notes for the detailed support of that, or even the textbook especially, right? But like, it's based around the idea that, you know, for starters, in terms of voltages and currents, you know, you might have a signal, a voltage source, or a voltage signal that looks like this right here, right? So it's at some value and it's going up and down, whatever. What we can do is actually break it down into two pieces, one of which is the large signal value, right here, and the other of which is the small signal value. When those are summed together, they become the total signal, right here. And we usually represent the total signal with a lowercase variable capital subscript. The large signal is capital variable capital subscript, and the small signal is small variable small subscript. And different components, based on their operation, end up having different types of small signal models. It just so happens that the MOSFET, when it's in saturation, which it will be for this problem, ends up looking just like this sort of thing right here, okay? A voltage-controlled current source. And this isn't too crazy because a MOSFET in general in saturation is a voltage-controlled current source. In fact, its expression, which describes how it operates in saturation, is just ID equals K over 2 VGS minus VT squared. Now, if we remember, K is just some coefficient of the MOSFET, and VT is also some coefficient of the MOSFET, the threshold voltage and the transistor constant, whatever you want to call it. VGS, importantly, is the voltage across the MOSFET gate right here, from the gate to the source. And then also remember, too, at the same time, this is assuming that the MOSFET is in saturation, and that has a couple stipulations about the voltage. In this class, if we say it's in saturation, it is in saturation. You don't need to worry about the fact that it's, you know, VDS is greater than VGS minus VT. But what we need to do here is, if we have a MOSFET, you can see it's a fun, but it's not a super easy to work with higher order function right here, and we need to linearize it essentially. And what we're going to do is take the Taylor series expansion of it. So what we need to do is, first of all, say, okay, ID is equal to ID capitals plus little id, right? So the big signal plus the small signal. And then that's really broken down into the following. It's going to be this expression, we'll do ID evaluated at, actually I'll draw a pipeline here, evaluated at the large signal input, so maybe at VGS in this case, plus the derivative of ID total signal with respect to the input, also evaluated at our large signal input, times the small signal voltage. This is our overall total small signal thing, right? It's saying basically your operation, the large signal output is based off of the whatever equation you have analyzed with the large signal inputs. In this case, the input is VGS, the output is current right now. And then the small signal, let me do a different color just to emphasize it. Let's do pink or purple. The small signal is based off of the derivative of whatever expression we're interested in with respect to the input that we're interested in, evaluated at the large signal input, and then times the input itself, the small signal input. This term will end up becoming what we call GM here, if we go back up to our model. Okay? So we need to analyze this out. It's not too bad. This expression, analyzed when VGS is capital VGS, that just ends up being K over 2 VGS, all capitals, the large signal input voltage, minus VT squared. The small signal one now, let's go jump at this and take the derivative of this expression with respect to VGS. This is not too bad. This is one of the few chain rules that's actually kind of easy to do, right? This is a second order 2 goes out front there. There's really no derivative on the inside, so it's a really simple chain rule. So this one, little id will equal K, the 2's cancel out, so you're left with VGS minus VT evaluated at VGS, the large signal, times little VGS. So if we evaluate this out, it's simply saying ID equals K times large signal input, VGS, all capitals, minus VT times little VGS. This term right here is actually what we refer to as our GM, okay, which is the term up here, interestingly enough. There's one other way with a MOSFET you can actually come up with your GM, and that actually is based off of the sort of looking at this relationship right here. So we can also see that if we were to take this and maybe drop it in and substitute it, we could also come up with an expression of the K's will cancel. We'll get 2 times ID over VGS minus VT times VGS. Also GM. These are equivalent terms. So depending on what inputs or outputs you know or have, you can use this one or this one. So now let's take this circuit that we have and let's convert it into our small signal equivalent. So I'm going to move down to this page. And what I need to do is redraw the circuit with only small signal components involved, including substituting in this symbol relationship organization circuit thing, whatever you want to call it, for this thing in here. And this includes all of the voltages and things too. So our input voltage is now just little vi. Our resistor coming in is still just a resistor. The small signal model of a resistor is a resistor. So R1. This is just going to go here and then end right at the gate. Then over here, we're going to have what? We're going to have, let's call this the drain. We're going to have a current source. And that current source goes down. Then it hits R3. And I guess over here we should make this go to ground just for reference. Then what do we got here? We have, so yeah, and this goes to ground. Good. Then R2, what is it? On the top of the transistor, we hit R2. Now, where does R2 connect? It connects originally to VDD, right? VDD is just a constant voltage, right? It actually doesn't vary at all. And because of that, right, we can say that VDD has no small signal element to it. So whereas the voltage here, the input voltage, was some large signal bias voltage, and then it wiggled around that, this one up here, our power supply, our VDD, doesn't have that. So actually, its small signal value is 0. And we can also, so that's done. And then let's just trace this one. R4 goes to ground here. And then, whoops, I don't need to draw that. But basically, this is still our V out, little V out. Now, because R2 is going to 0, it's the same as it's going to ground, right? So really, we could actually redraw this circuit. I'm going to copy paste it one more line down here. And let's delete some stuff to make what's going on clearer. And then what other things can we simplify, actually, if I'm looking at this? Sorry, I should have made this the source just for reference. And of course, sorry, I should have also noted that this is GM VGS. What other things can maybe be ignored? One thing to note is the voltage at VG is going to be based off of VI minus the current drop across the resistor, but since G doesn't go anywhere, right, we actually could say that the current here equals 0, right? So this resistor is actually not even needed. So we could just delete it and maybe just merge these together. That's nice. So that sort of simplifies our circuit a little bit. And then again, of course, this is GM VGS. And this is basically the small signal model or equivalent of the circuit up above, right? We've substituted in the MOSFET equivalent, right? This little current source. There's an input voltage of some value, and then we can see the resistors right here sort of collapse together, and they're in parallel. So this can actually, even simplify further to just what? The input small signal voltage to ground, G, then we could do nice and clean. I'm just going to draw one resistor because these are in parallel. So it's just R2, R4 over R2 plus R4. Very nice. That is the voltage out. And then, of course, this current right here, it's going to be based off of VGS and GM. So we go back and real quickly just add the D and the S so we get our orientation again, right? We should be able to just sort of quickly come up with an expression overall that maybe cleans up this a little bit. What I'm going to do is shift this over to the left. The only thing I don't like about this right now is this is a function of VGS, but VG we know. VG is going to be based off of VI, but VS is kind of weird because it's actually going to be itself a function of the current through here. That's going to get weird. So what we'll want to do is let's say that VGS, and again we're in small signal, will equal VI minus, it'll be little id times R3, right, because little id will be flowing down here. And again, this is with respect, this is our ground node, right? But we know ID is this, so we could say VGS equals VI minus GM, and GM was based off of the bias point values. VGS R3. So we could shift this over and we get VGS parentheses 1 plus GM R3. So VGS, little VGS, equals VI over 1 plus GM R3. Okay, so that's good. So actually we could even then go and, so that means our current source can actually be substituted for GM times this thingy right here. Okay, good. And really we don't even necessarily need the gate anymore. I mean, we might as well just leave it in there. But like this can really just be drawn as, I'm just going to copy paste it. Right here. Forget what VGS is because we've come up with an expression for it in terms of VI. So it'll just be VI over 1 plus GM R3 right here. Good. And so an expression for V out will equal what? It will equal negative this resistance times this current as a function. So it'll be negative R2 times R4 over R2 plus R4 times GM VI over 1 plus GM R3. Good. This is nice. This is actually the end of what I wanted to do with this one. So it's saying, you know, if we go back to the very beginning of this, right, you start with this problem, and in real life what you do is you put a voltage there, and that voltage would have a large signal bias value that would sort of position the whole circuit at a spot, and then there'd be a little bit of a wiggle voltage, and that would be maybe your information coming in. Now the position of the circuit based off of capital V, capital I, that'll dictate what VGS is, and sort of this large signal, and there's an ID. Those values together, depending on what you want to do, provide us with a GM value. Okay, so that's based off of the large signal GS. And we could also do, just like what right here, how we expressed VEI in small signal, or VGS in small signal in terms of VI in small signal, we could do an equivalent one in the large signal right here. We could come up with an expression and substitute VGS into with VI in some form, but it's actually a little bit more annoying to do, so I'm not going to do it. But nevertheless, from just a flow of information, right, we set a VGS here via VI. That VGS sets a ID, a bias ID, big ID. Then those two lead to a GM, and then that GM comes over here, influences the current source, like this, right here. As the small signal voltage comes in, it influences the current source as well. The resistors in the whole system, if we go back, R2 and R4, those end up being in parallel in the small signal model, and again, it's because there is no, the DC voltage, the VDD, has no small signal component, so it's 0, which is just a ground. They go in parallel as a result, and then our output voltage is just equal to this.